Hi guys, today we're going to be doing 9701, paper 43, October-November 2023. So question number 1, fluorine reacts with chlorine dioxide ClO2 as shown. F2 plus 2ClO2 forms 2FClO2. The rate of the reaction is first order with respect to the concentration of F2 and first order with respect to the concentration of ClO2. No catalysis involved. AI suggests a two-step mechanism for this reaction. So both of these steps will add up to form this equation. So F2 plus ClO2 form FClO2 plus F. You would need another FClO2 to form 2 FClO2. You would not need this F since it's not present in this equation. And you would need another ClO2 molecule to form this equation. So, in step 2, you should write F in the reactant side to cancel out for this F in step 1, plus ClO2 to add up, and FClO2 in the product side to add up. Or another way to answer this question would be F2 plus ClO2 forms F2ClO2, which cancels out with the reactant side of step 2, F2ClO2 plus ClO2 forms 2FClO2. And then later, balance the equation by placing a 2 because there's 2 fluorine. 1Cl, 1Cl, 2Cl. Okay. And then identify the rate determining step, which is the slowest step in the reaction, usually is the step 1, and explain your answer. This is because the first step has the same moles of reactants as the orders in the rate equation. Just now we read that the first order with respect to concentration of F2 and first order with respect to concentration of ClO2. So both of them are in first orders. So therefore, in step 1, they should have 1 mole of F2 and 1 mole of ClO2. Same as in here. You could also answer for the explanation same 1 mole of F2 and 1 mole of ClO2. And remember that F is not a mole. Next. When the rate of the reaction is measured in mole per dm cube second, the numerical value of the rate constant K is 1.22 under certain conditions. Complete the rate equation for this reaction, stating the overall order of the reaction. So, in this equation, there's actually a coefficient of 2 in front of the ClO2, but then usually you would write a 2 power in here, but then in this case you should not because rate constant is actually determined through experiment, and therefore rate is equal to K multiplied by the reactants. And then we can see here that the rate equation can only be determined through experiments and not from the stoichiometric equations or the coefficients of the chemical equation. So if you go back to the question, it says in the beginning that the first order with respect to the concentration of F2 and first order with respect to the concentration of ClO2. So from there we know that F2 is in first order and ClO2 is in first order. So therefore rate is equal to K power 1 and ClO2 power 1. Then the overall order of the reaction is the order of reaction of F2 plus the order of reaction of ClO2. So it's 1 plus 1 is equals to 2. So the overall order of the reaction is second order. Use your rate equation in I to calculate the rate of the reaction when the concentrations of F2 and ClO2 are both 2 times 10 power negative 3 mole per dm cube. So this is very simple. Just insert everything into the equation that we made here. Rate is equals to K, which is 1.22 as stated in the question, multiplied by 2 times 10 power negative 3 because of each F2 and ClO2 having this concentration, and power of 2 because one is for the concentration of F2 and the other is for the concentration of ClO2. Then you would get 4.88 times 10 power negative 6 mole per dm cube second. Usually, I would place it in 3 significant figures. Next question. C. Under different conditions and in the presence of a large excess of ClO2, the rate equation is as shown. Rate is equals to K1 multiplied by F2. The half-life T half, this is actually T half of the concentration of F2 is 4 seconds under these conditions. So this shows that the half-life is equals to 4 seconds. Calculate the numerical value of K1 giving its units. So for this question, because we are given with the value of the half-life, which is 4, and we are supposed to find K1, there's actually a formula for first order, which is T half, or the half-life, is equals to 0.693 over K. This is a constant at 0.693. So this equation calculates the rate constant with the half-life and only can be used for first-order reactions because first-order reactions have a constant half-life. So you would reorder this equation, forming K equals to 0.693 over half-life or over 4. You would get 0.173 and then three significant figures, 0.173. With the units s power negative 1 because time is in the denominator and this is in seconds, so s power negative 1. An experiment is performed under these conditions in which the starting concentration of F2 is 0.002 mole per dm cube. Draw a graph on the grid in figure 1.1 to show how the concentration of F2 changes over the first 12 seconds of the reaction. So in order to draw this graph, you should use the half-life information on the half-life that was stated in the previous question. So half-life occurs every 4 seconds. So it starts at 0.002 mole per dm cube concentration. So this is your first point. And then at the at half of 0.002, which is 0.001, there is an interval of 4 seconds. So this is your next point. And then next, at the half-life of 0.0010, which is 0.0005, around here, we have another half-life of 4 seconds, which is at the time 8, because this to here has the interval of 4. So your next point would be here, around here. And then 8 plus 4 seconds to 12, and which is at the half of 0.00005, around here I measured. And then I would draw a curve connecting them. I can't really draw a perfect curve as I've drawn with pencil here, so I'm just gonna leave it as is. Then question I, use your graph in figure 1.1 to find the rate of reaction when the concentration of F2 is 0.001 mole per dm cube. Show you're working on the graph. So to answer this question, because it actually says use your graph in figure 1.1, we are required to draw a tangent in order to get with the 1 mark. So we have to draw a tangent at the F2 concentration of 0.001. Here we have to draw a tangent, roughly a tangent that has equal sides in here. Then I would select 2 points. I selected, this one and around here. And then find the gradient of those 2 points. And then the gradient, I would get negative, ignore the sign, and I would get 1.684 times 10 power negative 4. 1.684 times 10 power negative 4. 3 significant figures. Here, this is the coordinates that I got. The answer key actually states that they would accept any from the range of 1.5 to 2 times 10 power negative 4. So because mine is within that range, it is accepted. Next question, question number 2. A. Define Kw mathematically by completing the expression. So Kw is actually the equilibrium constant for water. So from the dissociation of water, we know that H2O dissociates to form H plus and OH minus. And in an equation, it would form Kw is equal to products over reactants. So H plus and OH minus over H2O. And because H2O is always constant, the concentration of water is always constant, it is ignored, and there's only the final expression would be Kw equals to H plus and OH minus in these brackets with power of 1. Next, B is rather tricky, that's why it's 2 marks. 2 solutions V and W are described. V is HCl, W is NaOH. The concentration of HCl in V is the same as the concentration of NaOH in W. The pH values of V and W differ by exactly 11 at ATP or 298 K. I. Calculate the concentration of HCl in V. So the first thing that we know is the concentration of HCl in V is the same as the concentration of NaOH in W. So we can say that concentration of HCl is equal to concentration of NaOH. So H plus concentration is equal to OH minus concentration. And then we should form equations from that. So to calculate for the pH of HCl, negative log concentration H plus is the equation or the formula for the calculating the pH. And for pH of NaOH, it's a little bit trickier, which is 14 minus POH. 14 because its pH maximum is at 14 minus POH. We get the pH of NaOH. And POH is, when you insert here, is equal to POH is equal to negative log OH minus. So it's 14 minus negative log OH minus. And then we know the next clue is the pH values of V and W, or of HCl and NaOH, differ by exactly pH 11. So when you minus them, pH of HCl minus pH of NaOH is equal to 11. Then insert the formulas into this. We get negative log H plus minus 14 plus, because negative and negative cancels out, 14 plus log OH minus concentration is equal to 11. And because the log OH minus concentration is equal to H plus concentration as seen here, we exchange the log OH minus with log H plus. And so after we open the bracket, negative log H plus minus 14 minus log OH minus, interchange with H plus, negative log H plus minus negative log H plus, we move the negative 14 here, become plus 14. Negative 2 log H plus is equal to 25. Log H plus is equal to negative 25 over 2, or negative 12.5. And use maths rule of base power 10, base 10 to form power. H plus is equal to 10 power negative 12.5. So the concentration of HCl, or concentration of H plus, is equal to 0.0316 mole per dm cube. Next question. II. Equal volumes of the 2 solutions V and W are mixed, giving solution X. Name the solution X and state its pH. So HCl plus NaOH forms NaCl plus H2O. Name the solution X. Usually it would ask to name the compound. Don't actually write it as NaCl, even though the answer key in this case may accept it. it is preferable for you to actually state the compound, sodium chloride, name it. If it says identify, you can answer in the full name, sodium chloride, or NaCl. And NaCl actually has a pH of 7, neutral, because acid plus base forms neutral compound. Next, III. A 1 cm cube sample of 1 mole per dm cube HNO3 is added to a 100 cm cube of solution X forming mixture Y. A 1 cm cube of sample of 1 mole per dm cube KOH is added to 100 cm cube of solution X forming mixture Z. Estimate the pH of the mixtures Y and Z. No calculations are required. So we know that X is actually NaCl. NaCl at a pH of 7. And then a very large volume of NaCl is actually added. But then remember that NaCl just now has a very low concentration of 0.0316 mole per dm cube, because HCl to NaCl is actually 1-to-1 ratio here, 1-to-1 ratio. So it also has a concentration of 0.0316, which is very low concentration compared to the very highly concentrated here, HNO3, which is acidic. So if a very highly concentrated HNO3 is added to a neutral compound, NaCl, it would form mixture Y. What would you predict mixture Y's pH would be? So mixture Y would definitely be on the acidic side, and because this acidity has a very high concentration, you can assume that it is very acidic pH that is formed. So in the answer key, there is a range of pH 1 to 3. And then for the mixture Z, KOH, we know OH is a very alkali or basic alkaline or basic compound with a very high concentration compared to 0.0316 concentration of NaCl, which is neutral pH. So we can assume that mixture Z is very basic. And in the answer key, they give out a range of 11 to 13 pH. And therefore I answered 11 and 3 for mixture Z and Y. Okay, so next question. CI. CH3CH2COOH, which is this? CH3CH2COOH. CH3, next CH3, CCl2, COOH, and H2SO4 are all acidic. Suggest the trend in the relative acid strength of these three compounds. Explain your answer. So of course, the strongest acid here is H2SO4, because H2SO4 is a strong acid that fully dissociates. Meanwhile, you all know from AS level that organic acids are weak acids that partially dissociate. So now it's left with the organic acids. CH3CCl2COOH is actually more acidic compared to this because of the Cl groups. Cl- or halogen groups act as electron withdrawing groups, which are more electronegative and causes the O- ion or group to become less negative, and so the carboxylate ion formed here cannot react with H+, and the OH bond weakens, and therefore it breaks more easily. More H+ ions are released, and CH3CCl2COH is more acidic. And for this compound, CH3CH2COH, there's no Cl- group, halogen groups that could act as electron withdrawing groups, so that the OH bond can weaken and the H+ ions can be released. So it is the weakest acid here. Next, for next question, II. When concentrated H2SO4 is added to water, a series of acid-base reactions occur. There are 3 conjugate acid-base pairs that can be identified during the series of reactions. Write the formula of these 3 conjugate acid-base pairs. So, we can first write the equation between H2SO4 and water. H2SO4 is added to water to form H plus ion move here. This acts as an acid. This acts as a water is actually amphoteric, can act as a acid or base, but in this equation it acts as a base. H plus move to the H2O. H2O forms H3O2 plus, and H2SO4 forms HSO4 minus. And because HSO4 minus was an acid, it becomes a conjugate base later. And then because H2O was a base initially, it forms a conjugate acid, and always with a reversible sign. Next equation would be HSO4 minus reacting again with water, because there's still a H plus ion that could be lost from the compound. So HSO4 minus loses a H plus ion. Because proton donors are acids, it's an acid. Proton acceptors are bases, so water acts as a base once again. And then HSO4 minus forms SO4 minus only, which is a conjugate base because it was initially an acid. H2O forms H3O plus, initially a base, forms a conjugate acid. So this 3 pairs of conjugate acid base pairs does not necessarily mean that there would be 3 equations. There's actually only 3 pairs of conjugate base pairings in these 2 equations. So first is acid and conjugate base, H2SO4 and HSO4 minus. So let's do this. This and this. Then H3O plus here, because it says conjugate acid. Conjugate acid in this case is the one after, and H2O. And because there's another H2O here and H3O plus, so there's that pairing in both of the equations. And the final base pairing is HSO4 minus and SO42 minus. And list them all here, and you're done. And next for D, the partition coefficient Kpc of a substance Q between hexane and water is 7.84 at 298 K. So the value of Kpc is 7.84 at room temperature and pressure. Q is more soluble in hexane than it is in water. So we know that Kpc is equal to organic compound, which is hexane in this case, hexane's concentration divided by the aqueous compound's concentration, which is usually water. So first for I, define partition coefficient Kpc. This is usually something that you have to memorize. So Kpc is the ratio of the concentration of a solute between the 2 solvents of an equilibrium. The 2 solvents are hexane and water, and the solute is substance Q. So the substance Q is usually stated in the question whether it is initially placed in water or initially placed in hexane. But in this question, it just states that here, 5 grams of Q is shaken with a mixture of 100 cm cube of water and 100 cm cube of hexane at 298 K. So it's just immediately shaken. So we don't know that whether Q is initially in hexane or initially in water. It's just mixed in both of them. So to understand this, there's actually going to be a container where there is going to be contained hexane and water, which are 2 immiscible liquids, and then Q is going to be placed, and Q would either move up or move down. And in the question it says, the Q is after it is shaken with mixture of water and hexane, it is left until there is no further change in concentrations. So Q will go up or go down until equilibrium is reached. So calculate the mass of Q dissolved in the water. So if I am to assume that the mass of Q dissolved in the water is equal to X, then Kpc is equal to concentration of organic concentration first. So this is organic concentration. Concentration is actually equals to mole per volume, or it can also be equal to mass per volume. So in this case, I use mass, which is X grams over 100 cm cube. You don't need to convert it to a dm cube because it will cancel out below later, because 100 cm cube is present for hexane as well. So for hexane, 5 grams minus X is present. So in here, if X is present, 5 minus X is present. Then they total up to form 5 grams of Q. But this X is the mass of Q that dissolves in water. So we need to find X in this case. So this Kpc, 5 minus X, is X over 5 minus X is equals to 7.84, because Kpc mentioned here 7.84. We cross out the 100. X is equal to, we move 5 minus X here, and you open this and you would get X is equal to 4.434, or in three significant figures, 4.43 grams. This in the case if X moves up. If X goes down, if the mass goes down, such as in the answer key, the answer for this question should be 0.5656 gram or 0.566 grams. And your answer for this question would actually affect the next questions. So a sample of Q is shaken with a different mixture of water and hexane and left until there is no further change in concentration. It is found that the mass of Q dissolved in each solvent is the same. Use the Kpc value to suggest possible values for the volume of water used and the volume of hexane used. So this III question is a totally different scenario from the previous question II. So it states that Q is shaken with a different mixture and left until equilibrium is reached. It's found that the mass of Q is dissolved in each solvent is the same. So total 5 grams of Q is divided by 2.5 grams in each of the hexane and the water. So Kpc organic concentration is mass over volume, like just now. But this time we need to find the volume of hexane and volume of water. 2.5 divided by the volume of hexane over the 2.5 divided by volume of water. And then this is equal to the Kpc, which is 7.84 as previous. Then I can assume that the volume of hexane is equal to A, volume of water is equal to B. So 1 over A divided by 1 over B. You flip this, and it actually B over 1. B over 1. And then 1 over A times B over 1, B over A. So B over A is equal to 7.84. So we know that B, volume of water, to volume of hexane is 7.84 to 1 ratio. So you can actually use, from this ratio, you can use any volume of water and hexane, accepted any possible volume with this ratio. So in here, I chose 7.84 cm cube and 10 cm cube, which is within the ratio. Or in the answer key, if you use 0.5656 gram for the previous question, you can use 177.4 cm cube and 2.6 cm cube, which both adds up to 200 cm cube, which is the same total volume as the previous question, 200 cm cube. Next, IV. Q is more soluble in hexane than it is in water. It is suggested that Q is one of KCl, CH3, CH2, 4OH, which is CH3, CH2, 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 OH. This is this compound. Or HCOH, which is this compound. Identify Q and explain your answer. So in the beginning of the question, it says that Q is more soluble in hexane than it is in water. So hexane is a hydrocarbon with 6 carbon atoms if I'm not mistaken. 2, 3, 4, 5, 6. Then later there are the H atoms connected, and it is completely symmetrical. So it is non-polar compound. Non-polar compared to water. Water is O, and it is delta plus, delta minus. So it is a polar compound. So KCl should actually be the first thing that you should cross out from the list, because KCl is ionic and therefore it is the most polar. And we know that Q is actually a non-polar compound, because in order for it to be more soluble in hexane, which is a non-polar compound, Q has to be non-polar, because non-polar is attracted to non-polar and polar is attracted to polar. And so after we omit KCl from the options, we have either CH3, CH2, 4, OH, or HCOOH. We should now identify which is more polar of the two. So we know that actually HCOOH can form delta plus here, delta minus here, and form a more polar compound compared to CH3CH24OH. And so we can state that Q is CH3CH24OH because it is the least polar, and hexane is less polar than water, and thus they are attracted. Less polar with less polar forms attraction, and this 1 mark. And moving on to the next question, number 3. Hydrogen peroxide is a liquid at 298 K. It is moderately stable under room conditions but will decompose quickly if a catalyst is added. Reaction 1, 2H2O2 hydrogen peroxide forms 2H2O plus O2. So AI, define entropy, which is a measure or degree of disorder in the system. So for example, solid has, you could say, lower entropy than a gas. Something that has more disorder has a higher value of entropy. Number of possible arrangements of particles in a system. So predict the sign of the standard entropy change of reaction 1. Explain your answer. Sign is positive because it is more disordered. The liquid in H2O2 forms gas, and just now I said gas has more particles with a more disorderedness and more different possible arrangements of particles in a system in gas compared to in liquid, and so the sign is positive entropy. Explanation is because there are more gas particles in the products than in the reactants, or more molecules in products. Next question, B. Some bond energy data are shown in table 3.1. Type of bond, OO, OH, and stated in the table. Use the data in table 3.1 to show that the enthalpy change of the following reaction is negative 196 kJ per mole. So to understand this, we can actually draw hydrogen peroxide, O to O to H to H. O to O, there's 150. Then OH, there's 2, 460. But then because times 2, OO is times 2, 150 times 2. OH is times 2 times 2, which is 4. 4 times 460, which is the OH bond. Forms H2O, OH bond again, 460 times 2, but then because there is 2 H2O molecules, 2 times 2, so there are total of 4 OH bonds. 4 times 460 plus O and O, O2 is 496. From here, 2140 converts to 2336. And 2140 reactants minus products, 2336 forms negative 196 kJ mole. Rather than immediately doing reactants minus products, it can actually lead to a higher chance of carelessness. So I would prefer to put this yield sign first, then reactant minus products at the final calculation. Then next question, C. Some entropies, this is the sign for entropy, are shown in table 3.2. The enthalpy change and Gibbs free energy change for the following reactions are shown. These are the values. Use the data given to calculate the standard entropy of oxygen. So from the equation, if there is presence of Gibbs free energy, G is equal to delta H minus T delta entropy. Delta H is mentioned here. Delta S you should actually find. So first insert G. G negative 238 times K. Don't forget K. K is times 10 power 3. So negative 238 times 10 power 3. Delta H negative 196. Negative 196 times 10 power 3. And T is always in kelvins. So in here it's in standard room temperature and pressure. Here it's stated in the beginning of the question. So I've placed 298 as and the symbol of entropy. Then I calculate for the value of entropy 140.939. But then the entropy change is actually entropy of products minus entropy of reactants. It's always products minus reactants for entropy. So first is for H2O2 102. So 2 times 102 becomes 2 times H2O 70. 2 times 70 plus O2 is the entropy of oxygen. So the change in entropy 140.939 is equal to products 270 plus entropy of oxygen minus the entropy of reactants, which is 2102. Then I calculate, reorder the equation, then entropy of oxygen becomes 204.939 or round it up to 205, 3SF. Yes. Then D, the decomposition of H2O2 is catalyzed by aqueous iron III chloride and by silver metal. Identify by which of these two catalysts is acting as a homogeneous catalyst. So homogeneous catalyst is a catalyst that have the same state of matter or phase as the reactants. So the catalyst and the reactants have the same phase. So homogeneous catalyst in here is the aqueous III chloride, and the explanation is because it is a same state as the reactants in the equation or same phase. This is actually because silver metal has a state of solid. Iron chloride could be aqueous or liquid. And in here, the question, the reactants hydrogen peroxide is at liquid state. So iron III chloride matches the state of H2O2, and therefore it is the homogeneous catalyst. Next question, E. The E0 values, or E0 is also a standard electrode potential. So the E0 values for two electrode reactions are given. H2O2 plus 2H plus 2E minus forms 2H2O with an E0 value of 1 positive 1.77 V. And the second half equation is Cr3 plus E minus forms Cr2 plus with the E0 value of negative 0.41 V. So the first thing we should do here is to identify which of the E0 values is the cathode and which is the anode. Usually, the more positive the E0 value, the more positive it is, the further the equilibrium lies to the right, and so the less readily the element loses electrons and form ions. So this shows that the more positive the E0, we could assume that it is the cathode, and the less positive one, we can assume that it is the anode, and we should flip this equation because the electrons, as you can see, is in the reactant side. We should make it in the product side so that it can balance out with this. I. An electrochemical cell is constructed with the following half cells electrodes: an acidified solution of H2O2, a platinum wire, Cr2 plus mixed with Cr3 plus, a platinum wire. Identify the positive half cell. Positive half cell just now we identified is the first equation. So we could assume that the positive half cell is H2O2 and calculate the standard cell potential, or standard cell potential. We can calculate the standard cell potential by, I memorize it by E naught of the cathode minus the E naught of the anode. So positive 1.77 minus, when you flip this equation, the negative 0.41 actually turns into positive 0.41 V. So you could either do 1.77 plus 0.41, or you could do here E cathode is 1.77 minus unflipped anode, which is negative 0.14. So 1.77 plus 0.41 is positive 2.18 V. So to prevent any misunderstandings, we could say that add both E naught after flipping, and for this is the first method, and for this second method, don't flip the E naught. And when you don't flip the E naught, you can use this formula of E naught of cathode minus E naught of anode. Okay, moving on to the next question, II. Calculate the value of G, or Gibbs free energy, for the cell reaction that occurs per mole of H2O2. So the formula of Gibbs free energy, there are actually two formulas. One of them is this one, where the Gibbs free energy is equal to negative N times E naught of the cell times F. F is Faraday, and 1 Faraday is equal to 96500 coulombs. And then N in this equation, it represents the number of electrons present when we balance the two half cell equations in the beginning. So in here, 2 electrons, and then I would form this equation. I would multiply it by 2 so that the 2E minus would cancel out in either side of the reaction. So negative 2, comma, E naught of the cell is 2.18 as seen here, 2.18 times 1 farad, 96500 coulomb. Then I would get this, and because it's in K, which is K is times 10 power 3, I would disregard the last 3, and it forms negative 421 as the final answer. Moving on to the next question. F, the E naught values for two electrode reactions are given. H2O2 plus 2H plus 2E minus forms 2H2O, and CO3 plus E minus forms CO2 plus. For this question, I would disregard everything I've written here. Okay, an electrochemical cell is constructed with the following half cells. Half cell 1, an acidified solution of H2O2 under standard conditions, a platinum wire. Half cell 2, a solution containing 0.02 mole per dm cube CO3 plus and 2 mole per dm cube CO2 plus, a platinum wire. I. Use the Nernst equation to calculate the value of E, the standard electrode potential of half cell 2, under these conditions. So the Nernst equation is this: E naught plus RT over ZF, where Z is actually the number of electrons, times the log of bracket oxidized concentration divided by the reduced concentration. But then this value of RT over F is actually 0.059 for room temperature and pressure. So I would replace RT over F with 0.059. And then, rather than focusing on identifying which half reaction is the oxidized and which one undergoes reduction, I would rather use the method of log multiplied by left over right for standard electrode potential, where E minus is always on the left. So for example, if we are to use this equation where E minus is on the left, and it states that the solution containing 0.02 mole per dm cube of CO3 plus, so CO3 plus has 0.02 concentration, and CO2 plus 2 mole per dm cube, 2 mole per dm cube. So in this equation, the one on the left is 0.02, and the one on the right is 2. So we do 0.02 divided by 2. And then we insert the equation where E naught is equal to 1.82 V, 1.82 plus 0.059 over Z. The Z is the number of electrons, and in here, number of electrons is only 1. So multiplied by log 0.02 over 2, we get 1.702, or E is equal to 1.7 V. And for this question, we should know that Nernst equation is always for half equations only. It states in this question too, only for half cell 2. So don't focus at all on the half cell 1. So moving on, next question. Write an equation for the cell reaction that occurs in this cell under these conditions. So for this question, we should use the newly calculated E naught value of the cobalt half cell, which is 1.7 V. So let's rewrite this. If CO3 plus E minus is CO2 plus an E naught value of 1.7 V, and H2O2 plus 2H plus 2E minus forms 2H2O with an E naught value of 1.77 V. Both is positive. So which one of the half equations here is more positive? So of course it is this. Because this equation is more positive E naught value, it shows that it is the cathode. And because it's the anode, we should flip the equation. So once we flip the equation, we would get CO2 plus CO3 plus E minus, and because this is 2 electrons, we should multiply the whole thing by 2E minus, then cross this out. The new E naught value is negative 1.7 V, although you don't really need this right now. Cross out the 2E minus, and then you add them all up to get the overall equation, H2O2 plus 2H plus 2CO2 plus forms 2CO3 plus 2H2O, as seen in here. Okay, moving on. Next question. GI. Define the enthalpy change of hydration. So enthalpy change of hydration is the enthalpy change when 1 mole of gaseous ions forms an aqueous solution or dissolves in water. So enthalpy change of hydration is practically when ions dissolve in water and the ions form bonds with the lone pairs of the O in the H2O molecule, and when it forms bonds, energy is released, and that is practically the enthalpy change of hydration. So GII, aluminum fluoride AlF3 is an ionic solid. Complete and label the energy cycle to show the relationship between the enthalpy change of solution of AlF3, the lattice energy of AlF3, the enthalpy changes of hydration of Al3 plus and F minus. Include state symbols for all substances and ions. So the first thing we know is that lat is equals to enthalpy change of hydration minus enthalpy change of solution. We know that, and from there later it can be used to draw the arrowheads for the next question. So first we should define each of these points. So enthalpy change of solution is actually the enthalpy change when 1 mole of an ionic substance dissolves in water to give a solution of infinite dilution. So it is when ionic substance dissolves in water. So in here, solution, it is AlF3 solid forms aqueous ions of Al3 plus and F minus aqueous. Next, what is enthalpy change of hydration first? Hydration. Enthalpy change of hydration is the enthalpy change when 1 mole of gaseous ions dissolve in sufficient water to give an infinitely dilute solution. Hydration enthalpies are always negative. So, it is when gaseous ions dissolve in water. So, from the gas of gas ions form aqueous ions. Pretty simple. Then lastly, lattice. What is I could also name it lattice dissociation energy, because stating it as lattice energy is very vague. We should state whether it is lattice dissociation energy or lattice formation energy. So lattice dissociation energy or enthalpy is the enthalpy change needed to convert 1 mole of solid crystal into its scattered gaseous ions. So this is immediately from AlF3 solid to its gaseous ions, Al3 plus gas plus F minus gas. So in this case, lattice dissociation energy is from solid to gas, but then this arrow is from gas to solid. So we know that this is actually a lattice formation enthalpy, which is when 1 mole of solid crystal is formed from its scattered ions, and therefore this lattice formation enthalpy is negative. And just now the enthalpy change of hydration is negative. And actually enthalpy change of solution could be positive and negative. And because lat is equal to height minus sol, when it's gonna form like this, you can flip this arrow because it's minus sol. Okay, moving on to the next question. Relevant data for this question are given. Enthalpy change of solution of AlF3 negative 209, enthalpy change of hydration of Al3 plus negative 4690, enthalpy change of hydration F minus negative 506. Use this data in your energy cycle in GII to calculate the lattice energy of AlF3. So just now, lat is equals to height minus sol. Just insert them. Height is negative 4690 minus 3 times 506, because there when we balance this AlF3, we require 3 F minus ions, so 3 minus negative of solution, enthalpy change of solution. So we form negative 5999 enthalpy lattice energy. So negative 5999 or negative 6000. Okay, moving on to the next question. 4A. Cobalt II nitrate, CONO32, is a reddish brown crystalline solid. It dissolves in water to form a solution containing COH2O6 plus complex ions. Complete table 4.1 giving the formula of the cobalt containing species that is formed in each of the 3 reactions described. So I need to first fill in the table. This is through reactions that we have to memorize actually. Here you could see that I have inserted a Christmas tree that I have previously done for a project. And for this case, when CONO32 is reacted with NaOH or OH minus, it would form COH2O4OH2, as mentioned in the Christmas tree. But another way you could answer is COOH2, which is another option. However, from answer keys from previous years, they only accepted COOH2 as the answer when they react with OH minus. But because this is a recent paper, 2023, this should be also accepted. Okay. Reaction number 2 of cobalt nitrate with an excess of NH3, it forms CONH3 6 with 2 plus charge. If it's reacted with HCl, it forms COCl4 2 minus. II. Describe the color change seen in reaction 3. Original color of COH2O6 plus is pink. Then the final color after addition of an excess of concentration HCl is blue solution. This is memorization as written in the Christmas tree. Next, B. Calcium nitrate CaNO3 is a white crystalline solid. When heated, it starts to decompose at approximately 500 degrees Celsius. Write an equation for the decomposition of CaNO3. So this is just decomposition of metal nitrate. Metal nitrate decomposes into metal oxide plus nitrogen dioxide, or NO2 plus half O2. Or if half O2 or fraction coefficient is not accepted, you could multiply the entire thing by 2 so that you have no fractions, plus O2. Suggest temperatures, II suggest temperatures at which MgNO32 and BaNO32 start to decompose. Explain your answer. So because if we see in the periodic table, down the group 2, it's actually Mg, and then Ca, and then Ba. So it is increasing in size, as you can see in this diagram that I've drawn on the right here. So from this diagram, we can see that as we go down the group Mg, Ca, and Ba, the size increases. The atomic radii of Ba2 plus is far greater than Mg2 plus, and so larger cations like Ba2 plus polarize the nitrate ion less because it's of similar size, and so their polarization is not that much, and therefore they have stronger bonds that require a larger amount of energy to break. Meanwhile, Mg, a very large difference in size causes very much polarization to occur, and this causes bonds to break. Easier for it to break, and therefore a lower temperature is required to decompose MgNO32 compared to BaNO32. And because CaNO32 is in between them, Mg should actually have a decomposing temperature of lower than 500 degrees Celsius, and barium nitrate should have a decomposing temperature of larger than 500 degrees Celsius. As you can see, I've written 200 degrees Celsius and 800 degrees Celsius. The requirements in the answer key is actually for MgNO3 is less than 480 degrees Celsius. For barium nitrate, greater than 520 degrees Celsius. So you can't immediately put like 499 degrees Celsius for MgNO3 because it's too close to the decomposing temperature of calcium nitrate. Okay, moving on to the next question, number 5. Transition elements behave as catalysts and can form complex ions. Explain why transition elements behave as catalysts. This is actually something that you have to memorize because they often ask this question. Transition elements have more than one variable oxidation states, and they have incomplete d orbitals which can form dative bonds with ligands, which ligands are species that have lone pairs that can form dative bonds with a central metal atom. So B, Silver forms the linear complex ion AgCN2-. Copper forms the tetrahedral complex ion CuCN43-. Titanium forms the complex TiCl4 diers2 with a neutral charge, where diers is a neutral bidentate ligand. Bidentate ligand, sorry. Bidentate ligand means that the diers is actually bonded to forms two dative bonds to the central metal atom. So I state the oxidation state and the coordination number of titanium in TiCl4 diers2. So the oxidation state of titanium is actually 4 because diers have is neutral, and so it has a charge of 0. We should just focus on TiCl4. Cl has a charge of minus, and because there's 4 Cl atoms, so minus 4. X minus 4 is equal to 0, neutral, so X is equal to positive 4. Therefore, the oxidation state of titanium is plus 4. And for the coordination number, because Ti is actually bonded to 4 Cl atoms, we should actually draw that first, bonded to 4 Cl atoms, and then there are 2 diers. 2 diers form 2 dative bonds, so dier 1 and dier 2. So coordination number, how many dative bonds are formed? 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 coordination number. II. Draw 3-dimensional diagrams to show the shapes of AgCN2- and CuCN43- in boxes. Label one bond angle on each diagram. So first, we should actually already know that AgCN2- is actually a linear molecule, and a linear molecule has a angle of 180 Cn, and you could also add the total charge with an angle of 180 degrees. And for CuCN43-, from the 4 alone, we know that it's a tetrahedral shape. So we should draw it in 3D structure with this shaded and this, and then draw the angle of tetrahedrals at 109.5 at the charge of 3-, and done. C. The numerical value of the stability constant K stab of the copper I complex CuCN43- is 2 times 10 power 27. Write an expression for the K stab of CuCN43-. So first, we should actually make the equation for CuCN43-. So as you see here, this is the equation: Cu plus Cn minus 4. Cn minus 4 power 4 because it's 4, and the charge of Cn is actually minus, forms CuCN43-. So for every constant that we learn, it's always product over reactants. So we do products over the reactants, as you can see here. Okay, this question is pretty simple. Okay, moving on to the next question. CII. In a solution of concentrations of Cn- and CuCN43- are both 0.0010 mol per dm cube, use your expression from Ci and the value of K step to calculate the concentration of Cu plus aqueous in this solution. So we can see in the previous question that the value of K step is 2 times 10 power 27. So K step is equal to 2 times 10 power 27 products over reactants, where CuCN43- is 0.01, Cn- power 4, 0.001 power 4 times Cu plus, which is the concentration that we have to find, is equal to 2 times 10 power 27. So we can reorder this and then find for Cu plus, and we would get 5 times 10 power negative 19 mol per dm cube. Okay, D. A piece of a copper-containing alloy has a mass of 0.567 grams. It is dissolved in an acid giving 100 cm³ of a blue solution in which all the copper is present as Cu2 plus ions. An excess of Ki is added to a 25 cm³ sample of this solution. So first, there's a beaker with acid containing 100 cm³ of blue solution, and the blue solution has Cu2 plus ions, and then there is an alloy dissolved in this solution which has a mass of 0.567. We take out 25 cm³ of it and we react with excess of Ki. All of the copper is precipitated as white CuI solid and it forms white PPT of CuI. Okay. Cu2 plus ions are the only component in the solution that react with Ki aqueous. This is reaction 1. This reaction 1, the liberated I2 is then titrated. This I2 is then titrated with 0.02 mol per dm³ S2O32 minus. This reaction 2, the titration requires 20.1 cm³ of concentration 0.02 mol per dm³ S2O32 minus to reach the end point. Calculate the number of moles of I2 that are reduced in this titration. So this question for I, it talks about the titration. So we know that there is this V and there's this C. We can form C equals to N over V, N equals to C times V. So we can do 20.1 cm³. We form it into dm³, which is divided by 1000 times the concentration 0.02. Then we would get the number of moles of S2O32 minus here, and because it is in a 1:2 ratio, we would divide this S2O32 minus moles divide by 2 to form the moles of I2. So I2 have number of moles 2.01 times 10 power negative 4 when rounded off to 3 significant figures. So for II, calculate the number of moles of copper in the original piece of alloy. So in order to get this question is rather tricky, that's why I circled it. It's rather tricky for 1 mark question. So 2.01 times 10 power negative 4 is the mole of I2, and this is equal to the mole of I2 in reaction 1. So 2 times 10, 0.1 times 10, 2.01 times 10 power negative 4, you multiply by 2 to get the mole of Cu2 plus. Therefore, we get 4.02 times 10 power negative 4, the mole of Cu2 plus, which is in terms of a volume of 25 cm³. We want to find the alloy, which is the alloy is in 100 cm³. So 25 to 100 cm³, we would multiply it by 4. So the mole of Cu2 plus times 4 will form 1.608 times 10 power negative 3, which is the number of moles of copper in the original alloy, which is in the 100 cm³ volume. So we get 1.61 times 10 power negative 3. Calculate the percentage of copper in the alloy. So this question actually refers to the percentage by mass of copper in the alloy. So like how much copper is found in the alloy. What is the percentage of copper in the alloy? So we could do this by percentage by mass. First, find the mass of Cu2 plus. Here we already know the number of moles of Cu2 plus originally in the alloy. So we just need to find its mass. So because mole is equal to mass over mR, we can reorder this equation. Mass is equal to mole times mR. So the mole is previously 1.61 times 10 power negative 3 multiplied by the mR64, we get 0.102912 grams of Cu in the original alloy divided by the total mass of the alloy. Piece of copper containing alloy has a mass of 0.567. So this divided by 0.567 multiplied by 100, we get 18.2. Yes, 18.2%, or in the answer key it actually states 18.0%, rather similar depending on the MR that we use. Like here, I said, or if we are to use 63.5 MR for the MR of Cu, we would get 18.0%. So we should actually use this MR, not like how I did. I used 64. Okay, next, IV. Suggest why a solution of Cu2 plus is colored but solid CuI is white. So Cu2 plus has a charge of Cu2 plus, yeah. Meanwhile, the Cu in CuI has a charge of only Cu plus. So when you write the electronic configuration of this, first we should write normal Cu. Cu with no charge has the electronic configuration of Ar4s2 3d9. Variable oxidation states present because incomplete d orbital. Then when Cu plus, the electronic configuration is 4s1 3d10, which is a special case where the d is not where the d orbital is complete. Then Cu2 plus is Ar3d9, and therefore the first point we should get for answering this question is Cu2 plus is an incomplete d orbital, and therefore it's counted as a transition element and is colored compound, while Cu plus has a full d orbital. Full d orbital means that it is not a colored compound. And then the next mark goes from d electron promotion is not possible because electron cannot jump in Cu plus to a higher level to form a colorless compound. So D to D transition is not possible. Meanwhile, Cu2 plus, when the d orbital splits into two, it is possible, and therefore it can form a colored compound, which is the characteristic of a normal transition element. Okay, moving on to the next question. Number 6a. 5 ligands are listed in table 6.1. Complete the table 6.1 using the words monodentate, bidentate, and polydentate. So these three actually depends on the number of ligands present in each of these compounds. Each of these three words may be used once, more than once, or not at all. NH3 is drawn like this with only one ligand, so it's monodentate with one lone pair. EDTA4- is actually known to be a polydentate. CN- is a monodentate because of the lone pair in N, just like NH3. And this is known to be a tridentate if you count 1, 2, 3. 3 lone pairs. So dative bond can form in each of these lone pairs. C2O42- is actually a bidentate because of the lone pairs in oxygen. II. The molecule this is a tridentate ligand. Suggest the meaning of a tridentate ligand. Just as I mentioned before, have 3 ligands, so 3 dative bonds can form. We could say ligand that donates, tridentate ligand is a ligand that donates 3 lone pairs to a central metal ion to form 3 dative bonds. III suggests how this compound acts as a tridentate ligand. So we just state its action. The lone pair at each N group, we have to be specific. Where is the lone pair? It's at each of the N group, forms dative bonds. It's where dative bonds form. Next, B. Nickel forms the octahedral complex NiN2H2O22+. This complex can exist in 3 isomeric forms listed in table 6.2. One of these forms is a trans isomer. The other forms are 2 different cis isomers. So from here, we should identify complete table 6.2 using the terms polar or nonpolar. Identify 3 of these, polar or nonpolar. Each term may be used once, more than once, or not at all. So in order to answer this question, we could either imagine it or you can draw it to be easier. And there's 2 N's, there's 2 H2O. Okay. N, down. N, because it's tetrahedral, I'm drawing it in 3D structure. H2, H2O. Okay, so this is entrance where it's up and up. So because it's completely symmetrical when you draw it, H2O, H2O, completely symmetrical, and therefore it is a non-polar compound. Meanwhile, for the cis isomer, it's Ni connected to N, connected to N here, and H2O. Actually, it should be bonded to the O molecule, and then OH2. This can be mirrored to form a compound, which is the second cis isomer, H2O, H2O, and N. And this is the first cis isomer, second cis isomer, and because both of them is not completely symmetrical, there's a dipole in either there's a dipole going to a direction. That's why it is a polar compound. Okay, next, I describe the difference between cis isomer 1 and cis isomer 2. Like just now, I drew the reflected version. So they are actually both optical isomers. They rotate polarized light differently. So one goes clockwise, the other rotates anti-clockwise. Okay, next question, number 7. Sunset yellow is an additive used for coloring foods. A synthetic route for making sunset yellow is shown. Molecules E and G each contain one SO3 minus group. These groups are unchanged in the formation of sunset yellow. So first, we should draw the compounds E. As stated, the molecular formula. So this is pretty clear to be seen as a benzene, but then because benzene is normal C6H6, they lose 2 bonds when they are connected to either side. So this is, they lose the H atoms here and the H atoms here. It's cut with an R group, replaced with an R group, and therefore only have 4 H atoms. And in this case, it is bonded to SO3 minus and bonded to NH2. Pretty simple. And then they undergo step 1, which is not known yet. First, we should draw G first. G is C10H6. We know that it is this structure, which is actually called naphthalene. And naphthalene actually consists of 2 benzene rings that are fused together. And again, because it loses 2 H atoms, it's bonded one side with OH, one side with SO3 minus. And so it forms sunset yellow anion. And from this, we know that this compound is formed, and the rest of the compound is formed from here. So how do we form this compound from E? So of course we should undergo, so step 1 should be diazotization, where the NH2 becomes this, and triple bond N with the positive charge on the first nitrogen atom. And so it would form bonds with the G compound, the naphthalene, and form sunset yellow anion. Okay. A. State the molecular formula of the sunset yellow anion. So molecular formula doesn't require us to completely state like negative O3 as in order what it is, C6H4, and we shouldn't do that. Instead, we should just count all this, how many C atoms are there, how many H atoms are there, how many N atoms. So here we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. C16. H is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. H10, N2, O, 3, 4, 7. 7 as 1, 2, 2. B. Deduce the structures of E, F, G. I've drawn them. And then step 1. Suggest suitable regions and conditions for step 1 and step 2. Because step 1 is a diazotization reaction, we would require NaNO2 plus HCl to initially form HNO2, which is the region used to react with E to form F, and it has to occur at the temperature of 10 degrees Celsius or less, or else an unwanted mixture of products is formed. And step 2 is actually electrophilic substitution, because it involves an amine plus a phenol. So it requires the regions and condition NaOH aqueous or alkaline conditions required. D. Predict the number of peaks in the carbon-13 NMR spectrum of the sunset yellow anion. This actually means that how many carbon atoms have different carbon atoms with different neighboring environments. So how many of different environments of carbon? So it's like this. One carbon is different. These carbons have the same environment. So 1, 2. These carbons have the same environment. 3. This carbon has a different environment. 4. This carbon has a different environment. 5. Carbon has a different environment. 6. Carbon has a different environment. 7. Carbon has a different environment. 8. Carbon has a different environment. 9. This carbon actually has a different environment from this carbon, because it's not completely symmetrical, because there's a OH this side and there's no OH in this side. So it's counted as separate carbons with different environments. Carbon 10, carbon 11, carbon 12, 13, and 14 different environments of carbon. And so there are 14 different peaks of carbon-13 in the NMR spectrum. Number 8. Capsaicin is found in chili peppers. You should assume the CH3O group is unreactive in the reactions involved in the question. So name all the functional groups in capsaicin in addition to the CH3O group. So the first is phenol, then we have an alkene group, then we have an amide. An amide consists of actually NH, double bond O, and therefore the carbonyl group CCO is not actually a functional group. Okay, next, B. Complete the equation for the reaction of capsaicin with an excess of Br2 aqueous in the dark. Draw the structure of the organic product in the labeled box. So Br is actually an electron withdrawing species which activates the position 2, 4, and 6, and OH, the OH in the benzene takes priority in where to first start counting, and it's always clockwise from the OH. So OH is 1, 2, 3, 4, 5, 6. So Br could attach position 2, position 4, and position 6. But because 2 and 4 are taken by other bonds, Br can only attach to position 6. And so Br is attached to position 6, and another is the alkene bond breaks, double bond breaks, and then it forms Br bonds. And so there are 3 Br here, and another product is HBr from the release of H from the benzene. And so we should balance the equation by placing 2 as a coefficient of Br2. And next is C. Capsaicin is heated with an excess of hydrogen gas in the presence of platinum metal. The 6-membered ring reacts in the same way as benzene under these conditions. Draw the structure of the organic product formed. So we know that benzene actually reacts with hydrogen gas, benzene with hydrogen gas forms C6H12. So because we know that benzene is actually made of double bonds, these double bonds actually form bonds when reacted with H2, it forms single bonds. So it becomes cyclic compound. So this is the same for capsaicin. So we just need to open the benzene ring and it would form bonds, H bonds. Just draw the same structure without the benzene ring. And that's the answer. Okay. D. When capsaicin is treated with region J under suitable conditions, one of the product is methylpropanic acid. I. Identify region J and any necessary conditions. So region J is actually hot concentrated acidified KMnO4. So this is actually something that we learn in our AS syllabus, where when a double bond breaks, it forms this double bond. If, for example, let's redraw it. If double bond is formed with R and R, and this is H and R group, the double bond is broken when reacted with hot acidified KMnO4 to form CRR, which is a ketone, and COHR, which is further oxidized to form a carboxylic acid. And when the end of this capsaicin product is broken, this double bond is broken, it forms this compound C with OH, where C will form this compound, and therefore that compound is methylpropanic acid. And so the region J is hot concentrated acidified KMnO4. You should be complete and state that it is hot concentrated acidified to prevent risk of losing any more marks. So moving on, let's go to II. There are 3 different peaks in the proton 1H NMR spectrum of CH3, CH, CH3, COH, and CdCl3. D refers to a H atom, a H atom's isotope, which is deuterium with H1. So in here we are supposed to state the typical proton 1H chemical shift values for the protons, the splitting pattern, singlet, doublet, triplet, quartet, or multiplet shown by each peak, the explanation for the splitting patterns of the CH3 protons and the CH proton. So first thing you should do is draw this compound, CH3 bonded to CH, bonded to CH3 group, bonded to COOH. So for the splitting pattern, there's actually a formula N+1, where N represents the adjacent carbon atoms number of H atoms. So if we are to use CH3 is this and this. Each of the CH3 has a neighboring carbon atom bonded to one H atom, and therefore it is 1 plus 1 equals to 2, and therefore the splitting pattern is a doublet. An explanation for the splitting pattern is because there is one H on a neighboring carbon atom, and so the chemical shift values is 0.9 to 1.7 because it is the only CH3 group. Next, CH. CH is this, and it is bonded to a neighboring carbon atom with each 3 H atoms, and another neighboring carbon atom with 3 H plus atoms. So each methyl group has 3 hydrogen atoms. 3 plus 1 is equal to 4. However, you have 2 methyl groups, and therefore 4 times 2 is equals to 8. And therefore, you could say that it is a heptat, which is 8 splitting pattern of 8. Or you could say that it is a multiplet. Explanation for the splitting pattern is because there is 6 H in total on the neighboring carbon atoms. And therefore, CH has a chemical shift value of 2.2 to 3.0 ppm. That's because of this alkyl next to a C double bond O group. This represents that the carbon atom is bonded to more than one other bond. Next, COH. COH is special because it usually focuses on OH, and OH usually has a zero peak, almost no peak, and this is a rule. The proton is attached to O and does not have any splitting. Therefore, N plus 1 is 0 plus 1. Therefore, this is a singlet. So the ppm is 9 to 13.0 because it is RCOH, which is special. 9 to 13.0. Next, EI. Capsaicin is heated with an excess of hot aqueous NaOH. Draw the two structures of the two organic products H and K. So hot aqueous NaOH works to break the amide bond, and when it's broken, you split them into H and K, and we are going to draw it separately, where it is going to form, where when you're broken, this is gonna form H bonded to H, and this is gonna form C bonded to double bond O bonded to O minus, and then Na here will react with Na plus, and therefore NaO is formed, and this compound is formed. Name the two types of reaction occurring in EI. It's called hydrolysis and neutralization, or acid-base reaction. Because hydrolysis is first, hot aqueous NaOH breaks or hydrolyzes the peptide bond, and so later the OH is neutralized with NaOH, forming Na plus O minus. A salt is formed. Draw the structure of the organic compound or organic product L formed when capsaicin is treated with LiAlH4 in dry ether or dry ether, which is in a reaction of reduction. And LiAlH4 can work to form these reactions in the A-level syllabus. So carboxylic acid can be reduced to primary alcohol. Carboxylic acid can be reduced to aldehyde. Ketone can be reduced to secondary alcohol, and amide to amine. So the amide bond here, initially it was NH to COOH, can form an NH bond only, and the COH is gone, and therefore this is the structure. Next question, 9a. Benzoyl chloride can be made from ethyl benzene into two-step process. A reaction scheme is shown. So ethyl benzene, I draw the intermediate for organic compound M in the box. So first, ethyl benzene, this group is always to form benzoyl chloride, you have to form COOH here first, which is a benzoic acid. And no matter what this group is, it cannot form CH2COOH. It will always form benzoic acid. Benzoic acid is only bonded to COOH immediately from the benzene structure. And so first benzoic acid is formed, and then it undergoes a reaction to form benzoyl chloride, which is an acyl chloride. Suggest suitable regions and conditions for step 1 and step 2. Step 1, hot alkaline KMnO4 followed by dilute acid in a reaction called oxidation. See, any kind of alkyl benzene will form benzoic acid COH. And then step 2, it will react with SOCl2 or PCl5 or PCl3 plus heat. Choose one of them only, don't answer 3 of them. And the name of the reaction is nucleophilic substitution. Next, C6H5COCl, which is the acyl chloride, benzoyl chloride actually, reacts with phenol C6H5OH to give the ester phenyl benzoate. An incomplete description of the mechanism of this reaction is shown in figure 9.1. Complete mechanisms in figure 9.1 and include the relevant dipoles, lone pairs, curly arrows, and formula in the second box in the second product in box 3. So first, the lone pair is going to move to the C atom as this distorts it, and then because the lone pair is moved to C, a bond forms and the O forms a positive ion, and the bond moves to the O, and then another arrow here, and the double lone pair here moves to the bond to form this compound, and a bond where when the electrons here is donated to the O positive ion, the H is released, and so this bond is formed, and the Cl atom is also released, and the lone pair actually forms a bond here. So there's a double bond that is formed, and HCl is formed because H and Cl bonds together, H plus and the new Cl minus atom. Name the mechanism. It is addition-elimination reaction. C. Benzoyl chloride, chlorobenzene, chloroethane differ in the rates of hydrolysis when each compound is added separately to water at 25 degrees Celsius. Suggest the relative ease of hydrolysis of these three compounds. Explain your answer. So first, I would draw all three compounds: benzoyl chloride, chloroethane, and chlorobenzene. So the hardest to hydrolyze would be chlorobenzene. Why? Because chlorobenzene have a Cl atom which is bonded to the benzene ring, and this Cl atom will have a lone pair of atom that delocalizes the benzene ring. This is the same for phenol, where it is bonded to OH. The lone pair delocalizes the benzene ring or overlaps, and so it forms a more stable structure that is difficult to hydrolyze. So the CCl partial represents a partial C-double-bond-C character, which is very strong and is more stable. Next is chloroethane. Chloroethane is actually an alkyl group that donates. There's an alkyl group that donates electrons and conducts positive inductive effect to the Cl. So this alkyl group conducts positive inductive effect to the Cl atom. And finally for the benzoyl chloride, we all know that all acyl chlorides are actually very reactive in nature, and so it is the easiest to hydrolyze, because the C atom in the CCl bond is the most electron deficient, with this going here and another going here. And so the electrons in the C atom is very low, and so the CCl bond weakens and it is easier to break and hydrolyzes easily. And that's it for this video today. Thank you for listening.